Wonderful. It is
I will let you know
actually,
when you have 5 minutes left.
okay, thank you. Okay, it is actually about a seemingly naive question. How does torsion change the propagation of waves in general? Uh, it seems a naive question, but it is not. Actually, it gets us from pure math to observational predictions. The first point is that obviously we think all us know the wave the wave operator until we ask what it is, because the answer changes if you ask a physicist or a mathematician. If you ask a physicist, the standard answer is that one. Okay, that is the wave operator. But if you ask a mathematician, they will give you a different answer. They will tell you, no, it is the RAM operator, and both operators are not the same. Where this co-derivative is defined in that way, in terms of the Hodge dual and the exterior derivative. And the answer and the question is, well, who got it right? And well, it is the mathematicians, really. Both operators are related through something very strange, which is called the Weizenburg identity, which has this general form. It is a beautiful result, but in general, you will find it so poorly written that it is almost useless in the literature. So it is an aesthetical problem we have to solve first. And well, to solve that and discover the role of torsion here, we just need to introduce a bit of math. The first point, the first tool is this one. We have to introduce this operator, which is constructed through the Hodge dual and the Philbin one form. And it maps P forms in P minus Q forms. And in terms of this operator, we find that the code derivative has two generalizations when torsion is not zero and we are acting on fields with Lorentz indices. In general, these operators are the same when torsion is zero, but if not, they are different. And the strange thing here is that this alternative at the second line, it offers a Weizenburg identity, which can be written in a very practical, aesthetical way. That is the real Weizenburg identity. It is a very interesting piece of math. These operators satisfy an open superalgebra. And the interesting point here is that gravitational waves pick actually this second line alternative for the derivative and the wave operator. And for instance, the electromagnetic waves do not. They are completely unaffected by torsion. It is just about making the math here. In fact, if we consider gravitational waves, the first point is that you can see that if you make a perturbation on the Philbin, it has a Lorentz index. And that is the really important point here. The electromagnetic field does not, for instance. And let us consider, I mean, we can do this construction for any theory with torsion, but let us consider the simplest one, the Einstein-Carton theory. It could be interesting, for instance, if dark matter has a non-vanishing spin tensor. It could be a source of torsion. And in fact, it is a very nice explanation of the Hubble tension. In this case, it is the simplest case. And from all the polarization modes of gravitational waves, we can have only survive the two usual modes. So it is the most simplest case. And we can see that the equation for gravitational waves is written, in fact, in terms of this operator I have mentioned before in a very nice way. And also we find this new Roton mode there in the expression. Of course, if we want to study the behaviors of waves, we have to consider the Equinal approximation. It means we are considering waves which wavelength which is far smaller than the characteristic length of the background geometry. We make the standard things. We defined what we call a wave vector, but it is actually a wave one form, this k, which is there. And we decompose this in dominant terms and the deviations of geometric optics. And from there, we can define the amplitude and the polarization of the gravitational wave, for instance. And the result here is very interesting. At leading order, we get just a null a null vector, and it is a wave which is propagating on null torsionless geodesics. That is very interesting. It means that regardless of background torsion, a gravitational wave will always propagate on a null geodesic without torsion. And that is interesting. Regarding this aspect, it behaves as if torsion was not there, as it also does an electromagnetic wave. But it changes when you go to the subleading order. At that point, you find that the polarization of a gravitational wave is no longer a parallel transport along this null geodesic, but it is scrambled along this way through torsion. And we find another weird effect, and it is that the rate current density, which is saying how the amplitude propagates, also does not conserve, and it satisfies that. It means that torsion actually amplifies or dampens the gravitational wave along its path. It means that a careful measurement of both effects of polarization or amplitude may give some hint of how a background torsion could be. And that is interesting. Let us consider, for instance, torsion as a very weak effect scenario that, for instance, in some kind of merger, the gravitational waves are produced as in general relativity, but that, for instance, dark matter has some non-vanishing spin tensor and it induces some background torsion along the wave, along the propagation of the wave. And what it will produce, it is a tension. It is a tension between the luminosity distance measured through gravitational waves and the luminosity distance measured through an electromagnetic measurement through this expression you can see there. Where this integral is along the null geodesic, this eta is the conformal time from cosmology. And for instance, if you use the multi-messenger event from 2017, you can use it to constrain a bit one of the components of an homogeneous and isotropic torsion, and you can make that exercise. This integral we had before, in this case, reduces to this component of torsion, or this in terms of the redshift. And if you use this multi-messenger event, it has been the luminosity density has been measured through electromagnetic waves and through gravitational waves. And actually, the constraint is very bad because it is too close. Okay, it is like at 100 megaparsec. For a small zeta, you get that expression for this integral and this constraint for one component of torsion. I mean, it is just an exercise. If we could have further multi-messenger measurements, then we could constrain torsion much strongly. For instance, LISA is supposed to be able to measure events even to zeta equal 0.1. So it will provide a far better constraint for torsion.
5 minutes.
Okay, then let us jump to the conclusions. Well, there are two main results. One is pure math. One is about the Weizenburg identity. Now we can understand what it is actually, how it works, and why it works. And in the side of physics, we can see that background of torsion in general, I have shown this for the simplest theory, but it is a general result, will scramble the propagation of the polarization of a gravitational wave and will amplify or dampen the propagation of a gravitational wave amplitude. So, well, I'm hoping that with LISA we will be able to measure this kind of effect. And thank you very much.
Okay, thanks to you, Fernando. Are there questions or comments? We'll stop the timer here. Mauricio, please go ahead, and then Lucas.
Hello, Fernando. Thanks for the talk. Is LISA sensitive enough to detect this new effect?
It should be. Actually, you can see it here. For instance, now we are, if you see in this graph here, if you see in this graph, LIGO, the sensitivity of LIGO allow us to measure events really close to zeta equals 0. Here you can see it at the lower left corner. Okay, so actually the problem with that is that you cannot make a very good constraint of anything. Okay, you will need a much farther event, so the effect of torsion can work along the propagation of a gravitational wave. But if you can see it here in this graph, zeta 0.1 can allow us to make a much more good constraint in one of the components of torsion. Okay? It allows us to see which one of all these curves is the right answer. And if you don't have torsion, then it should be just a horizontal line, and you will have these two luminosity distance just equal, the electromagnetic and the gravitational. So it is actually to make a constraint. I mean, if you don't have torsion, if that is the answer, if, for instance, dark matter has a null spin spin tensor and it does not produce any torsion, then you can see it by this effect here. And that is the good point. I mean, it can indicate you if you have torsion, or you can refute it. Actually, that is the actual point of it.
Thank you, Fernando.
Thanks. So, Lucas, You also had a question, then Aros.
Yes,
Lucas.
yes. So thank you for the talk. And I have two very small questions. The first one is at the very beginning, you say that mathematicians have right. And
Yes.
so why is it so?
Okay. Well, that is a very nice question. Actually, it is because of the Maxwell equations.
Okay.
If you want to write the electromagnetic wave equation in terms of differential forms, it is just the RAM operator acting on F equals 0, or the RAM operator on A equals 0. So that is the real operator. And from this Weizenbach identity, you can see how curvature affects the propagation of an electromagnetic wave.
Okay, and so if you use the physicist Laplacian, you will need the Weizenbach identity to get the right equation for.
Exactly.
Thank you. And my second question was, can you expect to see an effect of torsion outside of dark matter? So can you expect?
Oh, yes, of course. Here I was considering the simplest case, just the Einstein Carton case. I'm thinking, well, maybe dark matter has a non-vanishing spin tensor, and therefore it could make up some torsion. But if you have a different kind of theory, for instance, some kind of Gauss-Bonnet coupling with an scalar field, it produces a very nice effect. If you impose the torsionless condition, you will have an anomalous propagation of gravitational waves, and they will propagate at a different speed than they actually do. But if you don't impose the torsionless condition, you can see that in this case, this coupling is a source of torsion, that the right propagation, that the right speed of propagation is recovered, and you can use all these math results in that context also. You can use these math tools in any theory you actually like. Actually, the problem here is the following. People have studied gravitational waves in theories with a non-vanishing torsion. The problem is that they just make a perturbation of the field equations, and they just study how they propagate. And if you do that, you just can work out after a very big effort only the leading order effects, but all the sub-leading order effects are actually impossible to get doing that. And that is why we created all these math tools in order to be able to access these other orders in the propagation.
Okay, thank you.
Thanks, Fernando and Lucas, for the discussion. Rodrigo, you have a question too?
Well, and I don't know if it's a question or a comment, but torsion is natural to occur because you have fermions. So basically you are saying that you believe dark matter is fermionic.
I mean,
or I'm wrong.
Could be. Yes, I mean, in case the dark matter are fermions, then you could expect that it will produce some torsion, and actually it has a very nice consequence, and it is that it explains very nicely the Hubble tension. Here I have the reference. Actually, it is a different work we made with Samuel, where it is. Here it is the reference 5. Actually, it is not about gravitational waves, but if the dark matter were fermions, and if it has a non-vanishing spin tensor, then it will explain the the Hall tension very nicely.
Yeah, but it will be weirder if it's not fermions. We have just one boson that is massive in nature.
Yes, I mean,
You're saying that's.
I mean, I like the idea of it being fermions and of dark matter creating torsion. I like that idea, but we don't know if that is the case. If they are a different thing, well, we can discover that through a measuring of gravitational waves. That is the idea. Is that I would like that, but we don't know actually if the dark matter are fermions or not.
Can I say something here? Because
yes.
The torsion, the totally antisymmetric torsion part is an action, is a pseudo-scalar. So part of the torsion could be the dark matter, as I also discussed.
Yes, exactly.
Talk. So
exactly.
it could be a pseudo-scalar, and it would be the torsion itself, plus the fermions that you would have.
Exactly.
So you may have more than one species of dark matter.
Yes, exactly. That is the point of this of the reference.
But it could be a scalar, pseudo-scalar, actually.
Yes,
it's totally antisymmetric part.
Yes, it could be.
Which would also couple to RR dual, to anomalies. It could also affect like the action coupling, say electromagnetic times FF dual terms. You could also couple there with have other optical activities.
Yes.
On the scalar sector.
yes. But the point is that we actually don't know.
Yeah.
And if it makes up some torsion, it could be a very nice way to discover it.
Well, in fact, your interesting observations is that what I mentioned as well, if the torsion is due to another field and it's only then in its antisymmetric part, then you will not see anything on the gravitational waves of electromagnetic fields. But if the torsion is fundamentally the geometry, you will. Otherwise, it would appear only as an action. That's an interesting.
Exactly. You are completely right. Here, this only this new plus component of torsion changed the propagation of amplitude. This completely antisymmetric piece does not. Exactly.
Precisely, because it's like an action.
And you say. Exactly.
If you have only this, then
exactly.
But you can distinguish experimental.
Exactly. You got mute. Sorry.
I was muted. I said absolutely. I agree.
Yes.
Sorry, I was muted.
Okay, well then, so we thank Fernando again